Let's run through some past climates, starting with this model reconstruction of the last glacial maximum. LGM, as it is referred to, has been a favorite target of paleomodelers because it provides a good recent big transition from a glacial maximum to the current interglacial. Interglacial generally refers to when we don't have these big ice sheets on North America and Europe, because as of now we still have glaciers on Antarctica and Greenland. So interglacial in that sense is kind of a definition that is accepted as these land glaciers missing. So looking at the various quantities from the model, it's looking at rainfall and temperatures. Again, we see cold temperatures, ice sheets. This is from a model from this paper here, and it wants to see if it's doing a reasonable job of producing not just temperatures but also precipitation, plus compare with all available data. This is what is always critical to validate against available data. And I'm not going to go into details, but this is just to give you an example of how models are actually run. And this is not a transient run in the sense it doesn't start from the Eemian, which was 130,000 years ago, where the radiative forcing started and the glacier built. It reached its maximum extent in the LGM around 21,000 years ago, and then the melting started. So this is just doing the last glacial maximum itself. There are details on how you set it up to do just that, but we won't go into that. This is a good example of looking at precipitation and temperature at various locations, starting with Greenland temperature, Greenland precipitation, North American temperature and precipitation, Beringia out here, Asia, Asia Pacific, Europe, Africa, and so on and so forth. So the idea is that model does produce reasonably the climate of the last glacial maximum, and then you can use that to see what was the ocean circulation doing, what was the ITCZ doing, what was the monsoon doing, and so on. So it is the way of filling in the process details that cannot be understood just using these paleoproxy data. That's the main use of the models. And then once you establish credibility, you can use them for future projections as well. Paleoclimate in general is all about past climates, but it covers the range from a few centuries to millions of years. You've probably seen the geologic timescale map somewhere. Hadean, Hades is a Greek word for hell. Before we discovered any sort of evidence of life on rocks and so on. That was the primordial soup phase, let's say, where lots of meteorites crashing into Earth, tectonics still very active, a lot of volcanic activities and so on. Archaeus is the beginning, where we get the earliest evidence of life around 3.85 billion years ago. And then you get Proterozoic, which is the early life. So that's where we know the earliest evidence of radially symmetric life in the Ediacaran and so on. The whole thing is called Precambrian because at 540 million years ago we get the Cambrian explosion, where something like 25 million new species suddenly appeared in the record, and that's called Phanerozoic, where the life is visible. So you have various visible evidences of life. We will look a little bit at the last 66 million years ago in the next couple of slides, which is the Cenozoic. So you have Paleozoic, Mesozoic, and Cenozoic. So you can zoom into that and look at the evolution of life growing from Ediacaran in the Proterozoic and Precambrian. So odd mesh-like creatures, fish, first organisms with shells. So you have to think about why shells would have evolved. Predation evolved at some point, so to protect against predation, they would have evolved shells, for example. Trilobites, first fish, insects. So when did plants evolve? When did flowers evolve? When did seeds evolve? When did pollinators evolve? All these are kind of very interesting questions. After the plants evolved, lots of carbon got buried in the Carboniferous, which actually created a global snowball Earth episode, as they are called. So that's where you get the large coal swamps, reptiles, dinosaurs came and went, and then you had flowering plants much more recently in the Tertiary, then extinction of the dinosaurs, and mammals began to dominate after that, and the humans arrived on the scene just at the last fraction of a second in this kind of time scale. But here we are discussing our impact on climate and Earth, because we are now the dominant species. So this is another way models can reconstruct past climate. We can use paleo dating and geolocating methods like magnetic lines to see where continents were in the past. For example, 175 million years ago, India is down here, Australia, and they slowly moved north, and eventually, as we know, some 70 million years ago, India crossed the equator and then started crashing into Asia, and the Himalayas arose because of that. So the oceans, ocean configurations, these shelf areas, which are very favorable for colonizing of marine species onto land, or evolution of new species because of upwelling, primary production, photosynthesis, and so on. Circulation can be produced in the models. These are critical because you also have to figure out which configuration is important or is more favorable for ice ages. For example, are low latitude land distributions more favorable because they can be in warm place and rain can accelerate the weathering, draw down CO2, or do you need land at the poles to create land ice and so on? Okay. This is another time scale going from the Cambrian to the present. Typically in paleoclimate, as most of you probably know, time runs from the back to the present. So you have Cambrian, Ordovician, Silurian, Devonian, and so on, down to now Neogenean, I hope. So Phanerozoic climate change is seen here in terms of delta O18. So remember that delta O18 corresponds to colder and warmer periods depending on how depleted it is. So here is the scale of that. So there are cold glacial periods marked with these depletion of delta O18 parts per thousand, and of course warm periods like the Cretaceous hothouse and so on. Okay, so that's a nice combination of looking at data and past climate reconstructions. These are again not transient simulations. You just specify land areas and you give it the energy from the sun of that time, which by now would have been close to the present, and then you let the internal dynamics evolve, where the ITCZ will go, where the upwelling will happen, what the ocean circulation and the thermohaline circulations will look like, and so on. This is another example of the history of the Cenozoic climate, so looking at the whole period, but then zooming into the last 80,000 years and last couple of millennia. This shows one of the strongest abrupt warming periods in the record, called the Paleocene-Eocene thermal maximum. We will revisit this a little bit. So as you go back in time, the number of wiggles decrease, for example, compared to here. So the time resolution of the records gets much weaker. So you will only resolve thousands of years, as opposed to here millennia or centuries, especially as you get closer here. And you can see also the if you go back 200,000 to 300,000 years ago, you can see that you have an apparent change in the time scale. Again, we are looking at delta O18. This explains how the various things are combined. So you have somewhat of a obliquity kind of time scale at 40,000 years, and then you have somewhat of an eccentricity time scale here, ellipticity time scale of 100,000 years. We will see that these time scales are not directly corresponding to the orbital time scale. So internally somehow time scales are being selected. There are various arguments that maybe this shift is not even statistically significant, or that the various ways in which the glaciers build and slide to lower latitudes, or the Copernican law about the area covered by the sun depending on the season or the distance from the sun. So when Earth is closer to the sun, it moves faster. When it's further, it moves slower. So it's not just the peak summer radiation, but the integrated energy over the summer that can be important. So just because you're closer to the sun doesn't mean you have more energy over the whole summer because you're moving faster. Whereas when you're further away or moving slower, so summer can actually collect more energy and so on. So those kinds of details we will not get into. But as you get closer here to 80,000 years ago, you can see many more wiggles within the wiggles. So you have the millennial, million year, 100,000 year type of time scales that you see here. But within that, you have many, many, many wiggles, and these numbers where they are actually colder. So you can see here Antarctic delta D deuterium is being used, which gives a similar signal as delta O18. So there are decadal to century timescale wiggles, which are called Danskard-Ushger events. There are also stadials and interstadials. There are colder events within that called Heinrich events, which are known for releasing glaciers into the North Atlantic and so on. So various time scales are found in the records, but not necessarily explained very well in terms of mechanisms. Okay, so what we are trying to focus on here is the perturbations and the timescales and the responses, so that we can extract what is most relevant for global warming timescales. The most important feedbacks that are typically looked at are water vapor feedbacks. Water vapor is a greenhouse gas. If you warm it, warm the Earth, water vapor is going to increase, which is going to trap more energy and warm further. If you make it colder, it gets drier. It's not as warm because of it. Reduced water vapor reduces the greenhouse effect. Lapse rate, which is the slope of the temperature gradient within the troposphere or the lower atmosphere. So that determines the stability of the system and how quickly it can rain and so on. Clouds, which can be positive or negative feedback depending on whether they are allowing solar or reflecting solar, how much outgoing long wave they are capturing, and so on. And of course albedo changes, reflectivity changes because of sea ice and snow cover and glacier building on land. Okay, so I will talk about additional feedbacks in the next podcast. This one is getting to 15 minutes, but as we said, the physical feedbacks are not the only feedbacks. We must worry about biogeochemical and carbon cycle feedback, because especially now we have increased carbon dioxide so much that carbon cycle feedbacks are dominating our fate into the coming century and longer, especially considering its residence time in the atmosphere, right?